Uh, 3 presentations till the party. Very exciting. I am, at least. I think definitely one thing you'll appreciate from my presentation is that I'll be standing here just for 15 minutes. So that's good as well. Because I've envisioned this presentation more like a lightning talk to try to convince at least some of you, the people that never really dealt to a greater extent with descriptive statistics, that's a good thing for us data scientists. I'll try to drag you under the surface for 15 minutes, get maybe a bit closer to the foundations, but hopefully you will resurface as a better scientist, better analyst. The mighty dwarf, descriptive statistics, I called it the mighty dwarf because it's not a big component of the data science ecosystem. It's rather small. But for me personally, throughout the years, I found it really mighty, really useful. And I want to share that. So the plan for the presentation is that I'll very quickly explain what the descriptive statistics really stands for. And then I'll go through 4 metrics that really worked out for me in the past. And my goal is that if at least you take one of the metrics with you today, that'll be a success. So what is descriptive statistics? Textbook definition. The type of statistics that are used to organize and summarize data. But really, what I find extremely helpful is that descriptive statistics allow me to summarize my data, my time series data, with the use of a single number, very informative number. And I come from a mechanical engineering or electrical engineering background where descriptive statistics is very popular, very used. But then as I went through finance and now with CodeWise in AdTech, I find that's not always the case. People don't really go back to the basics and maybe sometimes overcomplicate the tasks. So the intuition, descriptive statistics, arithmetical mean, summarizing data with a single number. Okay, simple. So I'll move to one of the metrics I really like. It's called the kurtosis. So I'll cut straight to the chase. I have this one in hand. Suppose we have a company running an online store and they're measuring the amount of sold goods as a function of time. So we have events in thousands on the y-axis and time in days. And so throughout the year, they were really happy or fortunate to have a normally distributed amount of goods sold. But at some point, an impulse appeared. Wow, what happened? And people, they did inside it, check what happened. It wasn't very, good for the business. And they thought, is there a metric that I could use in 1,000 of my shops that would always inform me that an impulse like that appeared? And I needed to be in the normalized way in a sense that I would always be informed about the extent of my impulse, regardless of the y-axis, whether it's millions or single units. I always want to have a normalized output from my metric. And this is where kurtosis comes in very handy. It's defined as the fourth standardized moment of the data, whatever. So what we have in this simple formula, in the numerator, we have the fourth moment of the data. It's called fourth moment. The first moment of the data is the mean. The second is variance. The third moment I'll talk about in a couple of slides. This one is the fourth moment. And in the denominator, we have a variance squared. And so when we apply the kurtosis on our signal, this is what happens. It's well-established knowledge that kurtosis for a normally distributed signal always revolves around 3. We can take it for granted, and it always increases in the presence of an impulse. That's good. So let's look at the amplitude distributions of the signals. Well, we can see that the left-hand side looks normal, whereas the right-hand side looks a bit peaked. It's got this peak in the middle. Obviously, nothing really changed in the distributions themselves. It's only the appearance of these two samples at the tails. But the perception of the histogram changes. This one looks more peaked. And so often, people think about kurtosis as a measure of the peakedness of the amplitude distribution. Funny thing, this shape is in the literature referred to as the platykurtic shape, whereas that one, leplokurtic shape. And one of the references from 1927 was describing this, yes, 27, was trying to help the readers remember these awkward sounding names, and so they used these two figures. This is an animal, it's platypus, short tails, fat body, whereas these two are just leaping kangaroos, which kind of sounds like leptokurtic. Funny, isn't it? The next one, CREST factor. So we have our kurtosis, and we know that the value of kurtosis will go up in the presence of an impulse. But what will happen if we had another impulse, but of slightly short amplitude? How do we want the metric to behave? So the kurtosis decides to go up. It says, well, I'm seeing more impulses in the signal. I better increase my size. And this is good in some circumstances. For example, I did my degree in monitoring the conditions of gearboxes in helicopters, and one of the things you're looking for is the amount of impulses in the signal, not that much in the amplitude. But some people may say, well, I want my metric only to go up if the higher speed goes up. So I don't really should use the kurtosis. I better use the second of the metrics, CREST factor. It measures the crest within the signal. It's defined as the peak of the absolute values within the signal divided by the root mean square of the entire signal. And so what happens if we throw the kurtosis on the signal? Well, it reacts to the onset of the impulse. Okay, the value went up, but it stays virtually the same for this one. Percentage-wise, the kurtosis reacted in 110% increase for the onset of the impulse, so for this signal, whereas for this one it went further up by 11%, whereas CREST factor, it went by 30% as reaction to this impulse, but it said, well, I'm not having that, I'll stay the same, or even I'll drop by very small degree. So this one, because of the very definition, it only monitors the degree of this, the highest impulse. Small difference, but sometimes helpful. The SKEWNESS. Once again, we have the signal that we saw with an impulse, and the kurtosis is 6.7. Well, a signal that looks dramatically, well, it's not dramatic, that looks different, has exactly the same kurtosis. Again, you wouldn't always want that. You want your metric to be describing very detailed what's happening within the signal. Again, looking at the amplitude distributions, this is the peaked but rather symmetric distribution, whereas this one kind of leans towards the left just because of this one impulse here. And this is what SKEWNESS is good at. It detects how skewed or how not symmetric the distribution is. It's the third standardized central moment. Kurtosis was the fourth. We were raising everything to the even powers, whereas here we're raising it to the odd power. So if something's negative, it stays negative. And the SKEWNESS, again, it's normalized. It will give us 0 if the amplitude or if the distribution is symmetric. It will move towards 1 if the distribution is skewed to the right. Now, I said skewed to the right, whereas this curve clearly leans towards the left, but when we're referring in this context about the skewness of the distribution, we're talking about where the mean of this distribution went, and because of that impulse it went slightly to the right, and so this curve is skewed to the right. Another metric that I find very useful, slightly different to the previous ones, it's called form factor. It's a metric that has very rigidly defined values for different shapes of waveforms. So I ripped this off Wikipedia, where you have different shapes of waveforms, sinusoids, rectangular, sawtooth, and you can trust in form factor that for each of these shapes it would output a very different value. And again, in many applications, that's a useful knowledge. You don't have to think about some fancy metrics of how to describe the shape of my signal. You just go with the form factor. In the real-time usage, imagine you're running this online shop and you're monitoring how often the user comes back to the shop and buys your stuff. If you see a user that throughout 100 days came back or was present in your shop just once and bought a good, that client is not of very big interest to you. But if you start seeing clients that are coming back to your shop and buy stuff all the time, the more often they come back, the more attractive they are to you, and maybe you want to start thinking about targeting them with some more adverts. And so form factor, it's a very good metric for that. It will have its maximal value for a single impulse in a signal, and it starts to decrease as the signal becomes more kind of evenly distributed, less peaked, as this example shows. We had a value of 10 for one impulse, and then it kind of went down to 6.2 for 3 visits, for 1 plus 3 and 2, so that's for 6 visits. And the kind of shopaholic that was on there all the time, just buying the hell out of the shop. Very useful metric. Okay, summary, good. I find descriptive statistics very useful, but for very specific tasks. The tasks that have the meaningful x-axis, most of the time it's the time, but it doesn't have to be the time. It can be just an order of the samples in your series. What's very good about great majority of the metrics from this domain is that they are normalized. It's easy to compare the metrics regardless of the y-axis, and that's super helpful for example, business analysts. Quick to calculate and a very well-established field, meaning loads of resources online, tutorials, very easy to get to the subject, and they are not that complicated as I thought you had the chance to experience. If you want to read about the couple of the slides in a bit more detail, you can just search my surname in KD Nuggets for a couple of blog posts, or just catch me after the presentation. Thank you.
Thank you, Paweł. Any questions? Oh, there is one there.
Thank you for this. Would you mind just showing the data again, the first slide of the data? So looking at that data, it looks like the underlying mean is quite constant. So have you tried these methods with more complex signals, like with trends or seasonalities?
Well, obviously, you will have to detrend the data somehow, remove the changes that occur maybe in a constant period of time. This is what's the name? Stationary signal. So the metrics stay constant over time. So if the trend is different, you may want to try, for example, just look at calculate the difference between adjacent samples. Just look at the differences between these samples and plot them. It'll be much more even. Oh, thanks.
Cool. One more question.
These metrics seem to be useful to describe the characteristic of the past signal. For example, how spiky is that spike, how fat is the tail, but can they be used to predict whether this spike will return sometime in the future?
No. No, I think you would have to look into some predictive models like the moving averages or the autoregressive modeling. Try to predict what will happen in the future based on the past samples. But these metrics, they just describe what happened and post-mortem analysis.
One more this way, maybe.
Do you use some kind of signal filtering, or do you work on raw data?
Mm-hmm. Well, it's all case dependent, isn't it? That's the part of cleaning the data. If you know that you get some stuff in your signal that's not really useful for your analysis, just get rid of it. But if you know that you should retain majority of the samples, you just keep them. You know, the better data quality you feed into your system, the better output you'll get. So just think about, you know, it's all in the data that I really want. If not, maybe try to subtract some frequencies. If the signal is periodic, you may want to do some Fourier transforms, get rid of some frequencies. But yeah, it's very case dependent. There's no recipe, no cookbook for that.
Okay, maybe one from me.
Mm-hmm.
Can you think about a specific example that this sort of descriptive statistics was helpful in your day-to-day job?
Well, when I was working on this condition monitoring, I was in the mechanical engineering business for 10 years. It was all about trying to describe the signal on the fly. So on a helicopter, Chinook helicopter, I don't know if you're familiar with Chinook with the two rotors, you get something like 156 sensors measuring the performance of the unit all the time. So you have to use these very quick metrics to be able to summarize what's really happening on board all the time. So kurtosis, it's one of my best friends, but the problem is people don't really say about that a lot. But with kurtosis, when you see one impulse, the kurtosis will react in increasing its values. But as you start to observe a lot of impulses like that in the signal, the distribution is likely to start to resemble a normal distribution again, and the value of kurtosis will drop again. So you have to be careful with these metrics and maybe test the performance on some synthetic data to really get to know your friend so it doesn't betray you in the worst possible moment. All right.
All right, thank you very much.
Thank you.
Very good.
Thanks.